So hi everybody. So it's lecture 8. Oh, actually, wait, I want to use. Okay. Okay, so the new thing is that I bought a tablet, so hopefully this won't crash anymore. Okay. So lecture 8. And before I begin the lecture, let me just recap the circle of definitions, theorems, and ideas that we covered in the last 2 lectures, because there's a lot, and sometimes it can just seem like one thing after another, and it's not clear how they're related. So I want to make it clear how what we've learned, how all the things are related. So, when we started talking about number theory, the key concept really is divisibility and the division algorithm. So the starting point is that if you have a number a, you can divide it by a number d, and you can write it as a equals dq plus r uniquely, where this number r is non-negative and strictly less than d, and this is called the remainder. So this is one concept. And a special case of this is when r is 0, and that means when a is divisible by d. So using this, we did a number of things. So we derived basic properties of modular arithmetic. Yeah, sorry for the bad handwriting. I'm still getting used to this tablet. So, this notion of A is congruent to B modulo M, which is, the same thing as saying that they have the same remainder modulo M, which is the same thing as saying that M divides A minus B. And then this had the arithmetic with modulo M had some interesting properties. So multiplication and we studied multiplication and addition, I suppose. So like this. We studied addition and multiplication. And improving the key properties of modular arithmetic, we used properties of the division algorithm. Now, another application of the division algorithm was when we studied the GCD of two integers, and in particular, we came up with a way of computing the GCD, namely the Euclidean algorithm, which was just sort of repeated application of the division algorithm. And then when we studied what this Euclidean algorithm actually does a little bit more closely, we got a nice bonus out of it, namely Bézout's theorem. Which says that actually for any 2 integers a and b, there always exist some integers s and t such that the GCD of a and b is equal to as plus bt. So this was done by just combining all the equations that you got from the Euclidean algorithm. And then using Bézout's theorem, we proved this simple looking lemma called Euclid's lemma. Which says that, well, if A divides BC and A and B are relatively prime, So if A divides BC and they're A and B are relatively prime, then A divides C. And now we are going to use this to prove a number of things in this lecture, but in particular, we're going to prove the fundamental theorem of algebra, and there are two parts of this, right? The fundamental theorem of algebra, there's the existence part and uniqueness. And I should say that there was another track that we kind of followed for a little bit in this chapter, which is we also used the division algorithm for a completely different application, which is how to compute binary and in general base B representations of integers. And then once we had that, combining this with these basic properties of modular arithmetic, we found this very efficient way to compute remainders of huge numbers by repeated squaring. So we had this repeated squaring algorithm. In particular, we have managed to compute 5 to the 45 modulo 7. Or I guess, okay, I should be careful about the brackets here. We computed the remainder of 5 to the 45 mod 7, so there's no need for the brackets here. Just computed 545 to the 45 mod 7. So that's a summary of what we've been doing. Now we haven't yet completed the uniqueness part of this theorem, and we're going to do that in a moment. But before we do that, any question about this sort of mind map or whatever this is? Okay. I want to make a couple of remarks about modular arithmetic based on some discussions I had in office hours. So here's one remark. So the remark is that we have two different notations related to modular arithmetic, right? So A mod M is a number, right? Is the remainder of A modulo M. So when you divide A by M, you get a remainder. That's A mod M. That's a number. A congruent to B parentheses mod M is not a number, right? What is that?
It's a congruence.
It's a congruence, but it's a proposition. It's a statement, right? Yeah, is a proposition asserting a relationship between two integers, A and B. Whoa, okay, this is some new thing that's happening with the stylus and not. Okay, let's erase this. Is asserting a relationship between A and B, between two integers, A and B. So be careful, these are not the same thing, right? The first one is an operation on one number, the second is a relationship between two numbers. And another remark, just to connect this notion of congruence with something we studied earlier, it's that this is a generalization of the notion of even and odd, right? So A is congruent to 0 mod 2. Sorry, this is 0. So let me make this very clear. If and only if A is even and A is congruent to 1 mod 2, if and only if A is odd. So all of this stuff, you can view it as a generalization of the concept of even and odd. So in fact, in general, if you have any integer n bigger than 1, we have that the integers are equal to S0 union S1 union S2 dot 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 up to union Sm minus 1, where Sk is the set of all integers that are congruent to K mod n. And these are disjoint. Sorry. Yeah, it's this. Okay, so once you fix an m, what you get, another way to conceptualize this, you get a partition of the integers into these m sets, like S0, S1, dot, 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 up to Sm minus 1. And each set contains the integers that are congruent to that number modulo m, that have that remainder. Actually, I should have used the other notation where I shouldn't say x is congruent to K mod m. I should say all integers x such that x mod m is equal to K. So that's the remainder of x when divided by it. And this is again for K going from 0 to m minus 1, because the remainder is a non-negative integer less than. Okay. So what we're going to do in this lecture is add more stuff to this picture. First order of business is to finish the proof of the fundamental theorem of algebra. In this lecture, we have three things. So one is finish the proof of the fundamental theorem of algebra. The second topic is what is division modulo m? So far we've talked about addition and multiplication, but what about division, right? So division, that means inverses, the inverse of multiplication. Modulo m. And the final thing is a special case of that, something particularly nice which happens when m is prime. So division when m is prime. And this is a named theorem called Fermat's little theorem, as opposed to Fermat's last theorem. So that's the plan for today. So let me begin by finishing the fundamental theorem of algebra. But any questions before that?
What do you mean by A mod m is remainder of a modulo m?
Well, I mean that it's the remainder you get when you divide a by m using the division algorithm.
Got it.
Yep. Okay, so let's finish the fundamental theorem of algebra. So there are two parts of this, namely existence and uniqueness. So first I'm gonna, so I actually proved existence in the last lecture, but I'm gonna give you a different proof of existence that I think is a little bit shorter, and it's a type of argument that we're also gonna use for later in the course. So I'll just show it to you. Let's see. Yeah, so I'm going to use a device which is going to come up later in the course, which is called the well ordering principle. So this is actually something from chapter 5, section 5.2, and this is an axiom. Okay, so we're not going to prove this. This is something we're going to take to be a true statement. And here's what it says. It says that if S is a non-empty subset of the integers, of the positive integers, sorry, then S has a least element. Okay. Now we actually used this argument for finite sets earlier. But the reason I'm explicitly stating it is that S could be an infinite set. And then, I don't know, things get a little murky when you're dealing with infinite sets. And there's actually no way to prove this from, whatever standard axioms we have already assumed. So we're just going to take this as an axiom that this is just a true statement. If you give me a subset of non-empty integers, it has a least element. So there's some integer in there that's less than or equal to every other element of that set. So I'm going to use this to prove both existence and uniqueness in the fundamental theorem of algebra. So that's existence and uniqueness of a prime factorization, where the factors are listed in non-decreasing order. So let's prove existence. So proof of existence of a prime factorization. So here's a proof. So let so let me just remind you what the statement is. So the statement is that every integer can be written as a product of prime numbers. What I'm going to do is I'm going to define a set. Let S be the set of positive integers such that n is bigger than 1 and n cannot be written as a product of prime numbers. Okay, this is a well-defined set. The set could be empty. In fact, if it's empty, we're trying to prove that it's empty, right? We're trying to prove that every integer bigger than 1 can be written as a product of prime numbers. But let's just consider this set of hypothetical counterexamples. I'm going to assume for contradiction that S is not empty. So assume for contradiction that this existence fails, that there is some number that bigger than 1 that can not be written as a product of primes. So now by the well-ordering principle, there has to be a least element of the set, right? By the well-ordering principle, S has a least element. Let's call it Q. Now, what can we say about Q? Can Q be prime?
No, because
no, because yeah, if it was
product.
Prime, it would be a product of primes. So since n is not prime, since Q is not prime, and now I'm going to appeal to lemma 1 from the previous lecture, which said if you have a composite, there's always some prime number dividing it. Lemma 1 from lecture 7, which I won't rewrite, implies that there is a prime that's called P, strictly less than Q, such that P divides Q. We proved this in the previous lecture. Now, can this, so this prime P, do you think it's in S or not in S? So what happens if you can write P as a product of prime numbers?
Then it can be written as a product of prime numbers, so it's not S.
Right. So well, okay, sorry, what am I saying? P itself is prime, right? So P can be written as a product of primes, namely just itself, right? But now so P divides Q. Actually, yeah, I should have asked a different question. That means that Q is equal to some C times P for some C, which is bigger than 1. And sorry, I should have asked the question for C. So is C an S? Do you think you can write C as a product of primes?
C must be in S, because if C wasn't in S, then C could be written as a product of primes, and then Q could be written as a product of those primes times P.
Exactly. So observe that this number C has to be in S, since otherwise C could be written as a product of primes. C is equal to some P1 through Pk for some primes P1, P2 up to Pk. And consequently, Q is a product of primes, right? And consequently, Q would then be equal to P1, P2, Pk times P, which is not the case, which is impossible since Q is an S, right? So C is an S, but now what's the problem?
C is smaller than Q.
Yeah, C is smaller than Q. So this is a contradiction. The way we usually write this contradicts the minimality of Q. So this contradicts the fact that Q was the least element. That's the proof. Okay, so we proved it a different way last time, where we said pick a prime, divide it out. Now you get a smaller number, and keep doing that until it terminates. And that's a valid proof. We'll formalize that in chapter 5. But usually a proof like that, where well, really it's called induction, where you repeat some process again and again, you can also replace it by proof using the well ordering principle. So any questions about this proof? Okay. So now let's prove the uniqueness part. So for the uniqueness part, we'll need a corollary of lemma 1, which I'll record now. Oops. Okay. So corollary is just a proposition that follows easily from a previous proposition. The corollary is if P is prime and P divides a product of some integers sorry, there shouldn't be commas here. P divides a product, P divides A1, A2, dot dot AK. Then P divides AJ for some J. It has to divide one of them. So if a prime divides the product of a bunch of numbers, then it has to divide one of them.
Is AJ in like the series of A1 to AK?
Yeah. So okay. Actually, let me specify this. So if A1 to AK are integers, and P is prime, and this divides for some J in this set 1 through K. Yeah, let's be more precise. Okay, so let's do a proof of this. So let's see, how should I structure this? So let me just write down lemma 1 since we're going to use it here. Lemma 1 is that if C is bigger than, if C bigger than 1 is composite. No, sorry. No, it's not a corollary of lemma 1, it's a corollary of Euclid's lemma. So let me remind you what Euclid's lemma is. Actually, Euclid's lemma is written on this slide here. If A divides B times C and A and B are relatively prime, then A divides C. So it's a corollary of Euclid's lemma. Let me replace that. Any ideas about how we're going to go about proving this? Like, how would this follow from Euclid's lemma?
Maybe assume there isn't, like from contradiction.
Okay. Yeah. So we can do this using the well ordering principle. It's a little bit awkward, but let's do it. So let S be the set of integers K such that there exists a counterexample to what I'm trying to prove. There exists a P prime, and there exists some A1 to AK such that P divides the product and P doesn't divide any of the numbers. Okay, so let's assume the statement is false. Assume there's a counterexample. And the clever part here is I'm going to look at the length of the product. I'm going to consider the set of lengths of products such that this is false. Now this is, so if assume for contradiction, the set is not empty. If it's empty, I'm done, right? If the set is empty, then I'm done, right? Then there are no counterexamples to what I'm trying to prove. So assume for contradiction. That S is not equal to 0. By the well ordering principle, S has a least element. K. And for that K, I have this example, right? So choose P and A1 through AK. So choose P prime and A1 through AK such that P divides the product and P does not divide any of the AJs, right? So now I'm in a good position to apply Euclid's lemma, right? Because what can you say about P and A1?
Since they don't, or since P doesn't divide it, can you say that they're coprime?
Yeah, they don't have any common factors other than 1, right? So like P doesn't have any factors other than Pn itself. So the only common factors of Pn A1 are 1, right? So since Pn is prime, the GCD of A and P1 is equal to 1. But now by Euclid's lemma, P has to divide the product of the rest of them, right? P divides A2 up to AK. And P still doesn't divide any of those, right? P doesn't divide A2 up to P doesn't divide AK. Why is that a contradiction?
Because P is going to be a string of that's shorter than our original string.
Yeah, exactly. This is now a counterexample with K minus 1 terms. That contradicts the normality of S. But now K minus 1 is an element of S, which is a contradiction. Okay, we're going to see another proof of this in chapter 5, but this is the basic idea here is something we'll see many times in this course. So this is a corollary of Euclid's lemma, that if a prime divides a product of a bunch of numbers, then it has to divide one of them. And now we can prove the uniqueness part. The proof of uniqueness. So assume there is a number that has 2 different prime factorizations, right? Assume there is an n bigger than 1 such that n has 2 different prime factorizations, p1, p2, all the way up to pk, also equal to q1, q2, all the way up to ql, where all of these pi's, I mean, let me just list them.
Wait, can you scroll up for a second? There's like something on the screen that kind of blocks the top. Okay. Thanks.
Yep. So assume there's a number that has 2 prime factorization, where p1 through pk, q1 through ql are our primes. Our primes. So now I'm going to do something that we did in the original irrationality proof. So if I have a prime factorization like this, so what happens if I have a number that appears on both sides?
We can just divide it out.
Yeah, you can just divide it out, right? So assume, without loss of generality, that pi is not equal to qj for every I and j. Otherwise, we could divide it out. Divide both sides by it.
What does this WLOG stand for?
Without loss of generality. Okay, so now I have this prime factorization into two different products of primes, and there are no primes in common. So I claim that with the corollary, I can finish the proof of uniqueness in one step. What's the key observation?
Left side divides the right.
Well, the left side divides the right because it equals the right. But actually, the first number on the left side divides the right side, right? Like P1 divides the right side because P1 times some integer is equal to the right side, right? So notice that P1 divides the right side. And P1 is prime. So now what does the corollary tell us? That we have a prime dividing a product of a bunch of numbers. It has to divide one of them, right? So by the corollary, P1 divides Qj for some j. But now Qj is prime, right? So what's the only thing that can happen?
Pi must equal 1 or Qj, both of which are contradictions.
Yeah, so the P1, actually, this is P1, must equal Qj.
Oh, P1, sorry.
Yeah, so yeah, you're right. So P1 cannot equal 1 because it's a prime. So since Qj is prime, this implies P1 equals Qj, which is a contradiction. So that's it. We have just proven the fundamental theorem of algebra, that every number has a unique prime factorization when written in decreasing order, non-decreasing order. So we just completed this last thing. And here the key input really was Euclid's lemma, which is a simple looking lemma, but we had to do all this song and dance involving the Euclidean algorithm and Bézout's theorem and whatnot to get it. But once we had it, we got the fundamental theorem of algebra. So any questions about this? Okay, so now we will move on to item 2, which is we'll talk about division. And there's a lot of cool open questions about primes. So I'm going to send you some like sort of popular science articles about it, which I think are very interesting by email. But now let's move on to item 2, which is division modulo m. So here's the key definition. So what is division? Well, it's the inverse of multiplication, right? Dividing is undoing multiplication. And so, okay, okay, these are just luckily not Zoom crashing issues, but just me getting used to this pen. Yeah. Okay, I'm just going to leave this here. I don't really care. Okay, so so division modulo m. So here's a key definition. So if you have a number that's not 0, then you can define 1 over that number if it's an integer, right? And now we're going to show how to do the same thing. We're going to define the same concept modulo m. So if a is not congruent to 0, modulo m, then an integer a bar is an inverse of a modulo m. Remember, you always have to keep this m in the background because modular arithmetic depends on what it's modulo. So it's an inverse if a times a bar is congruent to 1 modulo. Yeah. So it's a number so that when you multiply it by a, you get 1. So for example, let's look at an example. What is the inverse, or what is an inverse? We never said it's unique as defined so far. What is an inverse of a equals 5 mod 7? So that means, i.e., I want a number a bar so that 5 times a bar is congruent to 1. Right? By the definition, I want an integer a bar such that 5 times that integer is congruent to 1 mod 7. I'm mimicking what we do for, division over the real numbers, right?
Is that a equals to 5?
Yeah, okay, right. So this is not a congruence. I'm saying what is an inverse of the number a equal to 5 modulo 7? So, okay, maybe I'll just write it in English. So what I've defined here is the concept of inverse of a number, parentheses, mod m. So here a equals 5 is just, I guess I'm doing two things. I'm defining a and saying I want to look at the inverse of that number, mod 7. Is that okay?
Could a bar equal 3?
Well, could a bar equal 3? So let's guess a bar equals 3. Then you get 5 times 3 is congruent to 15, which is indeed congruent to 1 mod 7. So good. So this is an inverse. But this was a little bit guessing, right? So now we're going to answer two questions systematically. Question 1 is which numbers have inverses? Okay. Which numbers have inverses? Modulo m. It's not even clear that every number has an inverse modulo m, right? I mean, 0 obviously doesn't, but we don't know. And the second question is, how do you find inverses? So again, there is the gift that keeps on giving, which is the division algorithm and all of its offspring. So let's answer these questions. So I'm going to prove a theorem answering the first question. The theorem is if A and M are relatively prime, then A has an inverse modulo. Then A has actually a unique inverse. A inverse in this set, 0, 1, all the way up to m minus 1. So the uniqueness means that, so A, first of all, it's saying A has an inverse. Then it's saying if in this set, there's only a unique inverse, there's only one. Modulo m. So if they're relatively prime, then there's a unique inverse in that set. Any questions about the statement before I get to the proof? Okay, let's prove this. So there are two things, right? There's a existence, which is that it has an inverse, and then there's uniqueness, which is saying there's only one inverse inside that set. So let's prove existence first. So assume A and M are relatively prime. Now I need to produce an inverse, right? How am I going to do that? Let's go look at our little summary of everything we've developed. Which of these ingredients do you think could be useful? So I have to produce this inverse from somewhere, right? Do you see anything here that could help me produce an inverse?
Would Bezos' theorem maybe be helpful, since that uses the greatest common what's it called, divisor, or the Euclidean algorithm?
Yeah, maybe the Euclidean algorithm or Bezos' theorem. Bezos' theorem, it definitely produces something, right? It produces these numbers S and T, this linear combination, and they're related to the GCD. And we know we have to use the GCD somewhere, since that's our only assumption. So let's do that. Assume the GCD is this. By Bezos' theorem, we can choose.
Professor, I think your
Yes.
screen might be frozen because I just see the lecture 8 portion.
Oh man, I thought I had fixed this. Okay, fine. Okay, I'll be back in a moment. Everybody see it now? Yeah. Okay, good.
Yes.
Yeah. Okay. Yeah, it's kind of weird. It lasted a lot longer than usual, so I don't. Anyway. Okay, so assume so by Bezout we can choose some integers S and T such that the linear combination of A and M given by S and T, so AS plus MT equals the GCD, which in this case is 1. Okay, how is that going to be useful for finding an inverse? I'm interested in finding a number, so when I multiply it by A, I get 1 modulo M. What should I do with this equation?
Maybe take it modulo M. and
Yeah,
see
just
what
take the equation modulo M, right? If two numbers are equal, then they're congruent modulo M. So thus, I have that 1 is congruent to AS plus MT modulo M. But now I can simplify this, right? So AS is itself, but what's M congruent to modulo M? It's congruent to 0. So this is just congruent to AS. And I actually wanted this inverse to be in the set 0 to M minus 1. So S might not be in that set, right? So what should I do to S?
Take it modulo M.
Yeah, just take its remainder modulo M, right? These are the rules of modular arithmetic. This congruence remains true if I replace integers by their. This is S mod M.
I have a question.
Mm-hmm.
How did we know M was 0?
Well, what is M congruent to modulo M? what's the remainder of m when you divide m by m? Right, so we use that m is congruent to 0 modulo m. And that's just because m divides m, right? Does that make sense?
Yeah, thank you.
So now I'm happy, right? That's my remainder, S mod m. So this Bézout, this coefficient that I got from Bézout's theorem, that's S mod m, which is always less than m minus 1 and is non-negative, is an inverse of A mod below m. So this thing turned out to be extremely useful. So any questions about that proof? And this actually answers both question 1 and question 2, right? It tells me that, well, at least partially answers. It tells me if they're relatively prime, then there is an inverse, and it tells me how to find the inverse. How would I find the inverse? If I told you find the inverse of this number modulo m, what would you do?
The bottom line where you've written A times S mod M times mod M.
No. So that's one is congruent to A times S mod m modulo m.
Okay.
So this goes back to this remark I made, which is admittedly confusing. There are two different things, right? A mod m is the operation of taking the remainder, and A congruent to B parentheses mod m is a statement saying that A and B have the same remainder modulo m.
Okay. So is that like a reversal of A times S mod M is equivalent to A mod M times S mod M?
Yeah.
Okay.
So I'm not. I could have applied it to A, but I don't have to. Yeah.
Okay. Thank you.
So that's the proof of existence. Uniqueness. Uniqueness. I will leave this as an exercise. It's very easy, and it's a good proof writing exercise. You assume there are two inverses and show they're the same. It's a one-line proof. I leave it as an exercise. So that's it. So that answers, well, it kind of answers question 1. It doesn't exactly tell me which numbers have inverses modulo m, right? It tells me if they're relatively prime, then there is a unique inverse modulo m. But let me just state a fact, which I won't prove for now. It's not that hard to prove. You can try to prove this later. Is that if A and M are not relatively prime, then A does not have an inverse. I won't prove this. This is actually one of the exams on the practice problems on the practice midterm exam, which I will send you later today. So you can do this. It's not really that hard. But now with this fact in the theorem, and looking at the proof, I've completely answered these questions, right? Which numbers have inverses modulo m? Answer, integers relatively prime to m. And how do you find the inverse modulo m? Well, the proof tells me, right? You find these Bézout coefficients. And how do you find the Bézout coefficients?
Using Euler's formula?
Using the Euclidean algorithm.
Euclidean algorithm.
Yeah, right. So how is find a Bezout coefficient, S specifically, via Euclidean algorithm. You'll have several computational homework problems where you do this. So now we add one more thing to our little cartoon here. Is Bezout's theorem also gave me this characterization of finding in division modulo M. Like which numbers have inverses, namely those that are relatively prime to M. So now, I mean, okay. Is this clear, or are there any questions about this?
Could you give us an example of how to find
Sure.
like
Yeah.
the inverse?
Yeah. Let me just do the example that I started with, right? Find the inverse of 5 modulo 7. Let's do that using this method, right? So example, A is equal to 5, M is equal to 7. So indeed, these are relatively prime because they're actually both prime. So but according to the theorem, there is an inverse, there's a unique inverse, and you can find it with the Euclidean algorithm. So let's find it. So step 1 is find the Bezout coefficients. So step 1 is to apply the Euclidean algorithm. So 7 is equal to 1 times 5 plus 2. So I just keep dividing, right? Then I replace this by 5 and 2. So 5 is equal to 2 times 2 plus 1. And then 2 is equal to 2 times 1 plus 0. Okay, so now, so what does that mean? Well, it means the GCD is 1, right? Because that's the last remainder before I stopped. And now, if I use these equations in reverse, I have that 1 is equal to 5 minus 2 times 2. And now I'm going to use the formula for 2 that I get from this equation. It's equal to 5 minus 2 times 7 minus 5. So 1 is equal to, in this case, 3 times 5 minus 2 times 7. Right? So in the context of Bezout's theorem, what are my S and T here?
Three and two,
3 and minus 2.
or minus two.
So Bezout's theorem doesn't make any claim about the uniqueness of S and T, but it just says, just to spell it out, this is saying that 1, which is the GCD, is equal to, sorry, not 3, is equal to 5S plus 7T. Where S equals 3 and T equals minus 2. So now, according to the proof of this theorem, well, the inverse is just S modulo M. So the inverse is just 3. So therefore, the inverse of 5, right? So therefore, 5 inverse so let's see, I want to use the notation that the book is using for this. So let me just make sure I'm using the same notation. I'll just write it in words. I'll just say the inverse of 5 modulo 7 is 3, which is what we found out earlier, right? Or okay, we can use this 5 inverse is congruent to 3 modulo. So let's say it. I mean, I can define this notation this way, I guess, right? So the inverse of a non-zero element is defined in this definition over here. So I'm implicitly using this definition, right? And that's why I've written 5 inverse is congruent to 3 mod 7. Because if you multiply 5, and that's the same as the answer we got before, right? So yeah, so step 1 is the Euclidean algorithm, and then I suppose step 2 is oh, I was writing in blue the whole time. Interesting. Okay, so step 2 is just output S mod 7. It's not very difficult computation. Okay, any other question? Okay. Now, what's one implication of this, which we'll be talking about next time when we talk about cryptography? So here's an application, well, sort of a mathematical application, so I'll put it in quotes. The application is you can solve a linear equation modulo m, right? So can solve the linear congruence. So it's like a linear equation, except the equality is replaced by a congruence. AX is congruent to B mod M whenever, so X here is a variable, and that's unknown. Everything else is known. Whenever A is relatively prime to M. How? Any thoughts on how I would solve this? So if you just had to do AX equals B, like just the equation, forget congruence, how would you solve it?
You would divide each side by A.
You'd divide each side by A. But now we don't exactly have division, we have these inverses. So what do?
Multiply each side by A inverse.
Yeah. By multiplying both sides by A inverse, right? So if you multiply both sides of this equation by A inverse, you get another congruence. A inverse AX is congruent to A inverse B modulo M, but this is just congruent to X. So you can figure out, you don't find what X is, right? Because there's no unique solution. You could have infinitely many solutions actually, but you can find one solution. Okay, so that's all I want to say about division with a modulo M, where M is a general integer. But there's something very special and cool which happens when M is prime. And that's the topic of the last section. Which is inverses modulo prime. So this is one of the neatest proofs of this course. Maybe it's one of the real highlights. This is called Fermat's little theorem. And here's the theorem. says if P is prime and A is some integer that's not congruent to 0 mod P, so same conditions as in the previous definition of an inverse, then A to the P minus 1 is congruent to 1. Modulo P. Now, what does this have to do with inversion? Or let me just show you a numerical example before proving the theorem. Suppose P is 5 and A is 2. Then indeed, as the theorem predicts, if you look at 2 to the 5 minus 1, well, that's congruent to 2 to the 4, which is congruent to 16, which is indeed congruent to 1 modulo 5. Well, what does this have to do with inversion?
If we factor like an A out, we would get that A to the P minus 2 is the inverse of A for all A.
Exactly. So the upshot is it gives you a very simple formula for the inverse, which is different. You don't have to do Bézout's theorem and all that stuff. The upshot is that A times A to the P minus 1 is congruent to 1 mod P. So A inverse is congruent to A to the P, sorry, this is P minus 2. It's congruent to A to the P minus 2 mod P. So you can compute an inverse just by raising the thing to the Pth power. And this also explains a pattern that we see a lot in modular arithmetic, which is related to an observation somebody made in the previous lecture. The remark is, does this implies that the sequence A squared, A cubed, sorry, everything mod P. You take a number and you look at its powers modulo P, A mod P, A squared mod P, A cubed mod P, ... This sequence repeats. Because every time every P minus 1 terms, you end up just multiplying by 1, right? So this repeats every, I guess, P terms. Because every time you multiply by A to the P minus 1, it's just 1. You just get back what you had.
So in this theorem, yeah, it says that A is not congruent to 0 mod P. Why don't you just say A is not divisible by P?
That's fine. That's the same thing.
Oh, okay. I thought there's
Yeah.
like some difference.
No. It's exactly the same thing. A is not congruent to 0. I'm writing it this way to emphasize the analogy with division of real numbers, right? Because the only numbers you can't divide by are 0, right? So that's why I'm writing it this way. I'm trying to say if A is not 0 in this mod P universe, then you can invert it. This is a very different feature from what you see in real numbers, right? It's saying that you can reduce division to multiplication somehow, which is kind of funny, right? You can compute 1 over A by computing A to the P minus 2. So let's prove this theorem. Any more questions before we prove it? Okay. So the proof is quite subtle. And I'm gonna write the proof, then I'm gonna run the proof on an example just to make sure you understand it, because it's kind of tricky. Well, okay. So what's the assumption of the theorem? P is prime and A is not congruent to 0 mod P. So let's assume those things, right? So assume P is prime. And P doesn't divide A. Let's write it the way that you just said it. That's equivalent to saying A is not congruent to 0 mod P. So here's the sneaky thing about the proof. This is just a statement about A, but to prove it, I need to consider a bunch of other numbers. So consider the numbers 8 times 1, 8 times 2, 8 times 3, ... all the way to 8 times P minus 1. So these are now just integers. Okay, that's Z. Okay, well, you can see that, right? So how many numbers are in that list? P minus 1. And now consider their remainders. Remainders modulo P. So let's give these names. R1 is 8 times 1 mod P. So this is equality. This is not congruent. I'm defining R1 to be the remainder of 8 times 1 mod P. R2 is 8 times 2 mod P. ... In general, RK is 8 times K mod P all the way up to R P plus P minus 1. And these now all live in a smaller set. They live in the set 0, 1, all the way up to P minus 1, right? Why is that?
By like the rules of the division algorithm.
Yeah, they're remainders. So they're non-negative integers between 0 and P minus 1. So far, I haven't done anything non-obvious. But now there are two interesting things that happen. So this is claim 1. So claim is, again, just a proposition. But sometimes within a proof, we want to include, a little proof of a little mini proof, like a subproof. So we use the word claim. Claim 1 is that none of these are 0. Okay. So RK is not equal to 0 for all of these, for every K. So none of the remainders are 0. Proof. So it's a proof within a proof. That's okay. It's a proof of the claim. Well, let's assume for contradiction that it is 0, right? So if A times K, so if A times K mod P is 0, then P divides A times K, right? Okay, what should I do next? So P divides A times K. What do I know about the relationship between P and A?
P doesn't divide A.
It doesn't divide A, yeah. So P and A are relatively prime, right? So what tool can I apply now to this situation?
P must
Euclid's
divide
lemma.
K.
Euclid's lemma, yeah. P must divide K, right? P and A are relatively prime. P divides AK. Euclid's lemma, so P has to divide K. Right, so let me write it here. So since the GCD of P and A is 1, Euclid's lemma implies that P divides K, which is impossible because K is less than P, right? That's a proof of the claim. Claim 2 is that these numbers are all distinct. Claim 2 is that RK1 not equal to RK2 whenever K1 is not equal to K2. So these numbers are not 0 and they're all different. Proof, I'll skip in the interest of time, but it's also just Euclid's lemma. Similarly easy. So these are my two observations regarding these numbers. And now let me just do a little numerical example, just to here's a running example. The running example, let's use the P and A we had earlier. P equals 5, A equals 2, right? So I consider the numbers, 2 times 1, 2 times 2, 2 times 3, and 2 times 4. Then I look at the remainders modulo 5. So the remainders are R1 equals, so 2 mod 5 is 2, R2 is 4, R3 is 6 mod 5, which is 1, and R4 is 8 mod 5, which is 3. And indeed, these numbers don't include 0 and they don't repeat. Okay, so now I'm going to do something really sneaky. Here's a sneaky idea. Usually you don't write sneaky idea in the middle of a proof, but I want to emphasize that. Sneaky idea is we will compute the product of these numbers in two different ways. The product of the remainders, R1, R2, all the way to RP minus 1 in two different ways. This is a very common trick in math. Compute the same thing two different ways. Sounds like it shouldn't do anything, but it actually often is very powerful. So first, by claims 1 and 2, I know what the product is, right? Well, each number between 1 and P minus 1 appears exactly once in this list of numbers. So when I multiply them all together, what am I going to get?
P minus 1 factorial.
P minus 1 factorial. The order doesn't matter. So I get 1 times 2 times 3 all the way to P minus 1, which is P minus 1 factorial. So in particular, this product is congruent to P minus 1 factorial modulo P. Second, I'm going to do something a bit more basic. Where did I get these numbers? Well, I got them by taking A times 1, A times 2, A times 3, etc., and taking the remainders mod P. And the key principle of modular arithmetic is it doesn't matter if you take the remainders before doing the arithmetic or after. So I have that R1, R2, RP minus 1 is congruent to A times 1, times 8 times 2 all the way up to 8 times p minus 1 mod p. And now I get a different answer. I get a to the p minus 1 because they're p minus 1 numbers times p minus 1 factorial. This is the beauty of computing the same thing two different ways. If you get different answers, you learn something. So what's the conclusion when I combine these observations? Thus, a to the p minus 1 times p minus 1 factorial is congruent to p minus 1 factorial mod p. Now I'm almost done. I'm not quite done because I wanted a to the p minus 1 is congruent to 1 mod p, right? That's what it says over here. But now I have the same thing, but with both sides multiplied by p minus 1 factorial. So how do I get rid of the p minus 1 factorial?
We showed that it's relatively prime to p.
Yeah, right? So observe that p does not divide p minus 1 factorial by the corollary, actually, to Euclid's lemma. So actually p minus 1 factorial has an inverse. Let's call it, I don't know, I modulo p. And now if you multiply both sides by I, so multiplying both sides by I, both sides of the congruence, you get a to the p minus 1 congruent to 1 modulo p as desired. Okay, so it's a very sneaky proof. You have to somehow dream up this idea to compute this product, and you have to compute it two different ways. And this is the easiest way to prove this, actually, but it's a really remarkable fact that we'll be using a lot in the next lectures. So anyway, that's the end of today's lecture. As I announced, midterm 1 is next Tuesday. It's a 24-hour exam, and there'll be a practice midterm posted today.